last video, we started answering the question, why do we need calculus, and we went over the area problem. As promised, in this video, let's shift gears and talk about the tangent problem. Suppose in the not too distant future, you are the owner of a brand new car that is very green and wicked fast. You decide to go for a ride to a friend's house, but when you arrive at your destination, you look at your phone only to realize that a speed enforcement drone has sent you a notice that you've been ticketed. The car is fast, but irresponsible and you don't remember speeding. You notice the time on the ticket and decide to check the car's interface to see how fast you were going at that time. Unfortunately, the car was expensive, so you only sprung for the base model, and the only useful metric you can find is this distance versus time graph, a huge oversight of engineering. Now, you recall that the average velocity can be calculated by taking the change in distance and dividing it by the change in time, so that when looking to calculate the average velocity of the entire trip, you're looking at the slope of a line that passes from the very first point of your trip to the very last. But how do you get the exact velocity at the time you were supposedly speeding, shown by the blue dot? Whether you realize it or not, what we are actually looking for is the slope of an imaginary line that is exactly tangent to our point of interest. If we can find the slope, we find our velocity and either confirm or dispute the drone's claims. The only problem is, to calculate slope, we need 2 points, not just one. After thinking about the problem for a few minutes, you realize that we can approximate the slope of this point by picking another point somewhere along our curve. Let's use mathematical syntax to help us model the situation so far. We have our blue dot, point P, and now we have our second, arbitrarily chosen red dot, point Q. Each of these has a T position for time and a D position for distance. For point P, let's call our T position A. Our D position can be found by plugging A into the function that gave us this curve. Therefore, our D position can be called f at A. Similarly, for point Q, let's call our T position X and our D position f at X. If we draw a line between these 2 points, we notice that as we move our red point Q closer to our blue point P, our approximation of the tangent line we saw earlier gets closer and closer to the right position. We know that the slope of that line is going to equal rise over run, or change in distance over change in time. So using the mathematical representation we chose, we know that the slope of our line is proportional to f at A minus f at X over A minus X. Since we observe that the closer our point X gets to A, the more accurate our approximation of the slope or velocity is, we can say that the slope of our tangent line is the limit of the slope of our approximate line as point Q approaches point P. Don't get confused by the math and symbols here. This idea makes sense. The closer we get to the exact time that the drone took our picture, the closer we get to the instantaneous velocity at that exact moment. So as our arbitrary time x gets closer to our time of interest A, we get closer to the true velocity. Once again, don't worry too much about the limit notation just yet. Just try to wrap your head around the problem. Now, I know the drone car situation is pretty unrealistic, but I hope that you can see how this kind of problem is, once again, pretty exhausting to solve. Thankfully, we have another tool that can help us do this kind of work much more efficiently and much more accurately, namely, a branch of calculus known as differential calculus. Differential calculus is largely concerned with the concept of rates of change, and it has tons of applications across natural and social sciences. I hope that by seeing the area and tangent problems, you're beginning to see the limitations of our mathematical knowledge so far. Answering what seems to be very simple questions can turn into complicated, labor-intensive tasks. That is why we need calculus. It opens up the door for us to be able to tackle a whole new range of problems that would otherwise be very difficult, if not impossible, to solve. Now, I know we didn't really get into a whole lot of calculus, but I hope that this makes you excited to begin the journey of understanding calculus, so that when we see these types of problems in the future, we know exactly how to tackle them with the best tools available to us. If you enjoyed this content, please like and subscribe. Stay curious, and I'll see you in the next video.